The last part of this chapter is a little more straightforward than the previous screencast and shouldn't take us long. We're going to look at what is meant by the bond order, then the bond length, and then bond energy. And especially when, in terms of length and energy, you should be able to anticipate trends as you go from left to right, and of course as you go from top to bottom. Now, the order of a bond, highlighted here in yellow, is pretty simple. If you have a single covalent bond, it's bond order 1. If you got a double covalent, its bond order is 2. Triple covalent, that bond order is 3. But the interesting thing is you can get some fractional bond orders, which gives you an indication that this concept of bond order is a bit artificial. In any case, to give you an example of the easy ones, in CH4, methane, every single bond is a bond order of 1, first order. In carbon dioxide, both of your carbon-oxygen bonds have a bond order of 2. In Brinkelhoff nitrogen, you have a bond order of 3. Pretty straightforward. But what about in a resonance structure? If I take ozone, and I'm going to redraw it here, with single covalent bonds to each of my other 2 oxygens, and I'm going to take away a pair of electrons. In other words, I'm taking that pair of electrons and I'm taking that electron from the double bond, and then I'm going to take those electrons and I'm going to distribute them around here so that the left side looks just like the right side. It's symmetrical from left to right. It's not symmetrical, of course, from top to bottom, but it is symmetrical from left to right. So we do have a bit of polarity here. But in any case, this region of negativeness, and I'm going to pick a different color to show it, this region of negativeness there and there has a single covalent bond and then a pair of 4 electrons that are kind of distributed over the entire molecule. So that's actually a bond order of 1.5, or 3 halves, which is 1.5. And the way you can calculate bond order, if you don't like doing the drawing method, which I just did, is when you look at ozone, and let me go back to my blue color and also erase this. When we look at the ozone molecule as drawn in this picture, one of the resonance structures, you can see that there are 3 covalent bonds, 3 XY bonds. There's one right there, one on the top and one on the bottom, for a total of 3 bonds the way it's drawn there. And then the number of XY links is you have a link between this oxygen and this oxygen, and you have a second link between this oxygen and that oxygen. So you have 2 links. And that's another way of coming up with a bond order when it's going to be fractional. Now, the bond length. How long is the bond? Which, of course, is going to be reflected in the size of the molecule and the space between the atoms within that molecule. So the bond length is defined as the distance between the nuclei of the bonded atoms. Obviously, there's no solid outer shell surface, but the nucleus is pretty compact and dense, and so we can talk about to the center of the nucleus as being how we're going to measure distances. It would be the same way that we would measure distances between planets or stars, for example, from the center of one to the center of the other. And obviously, again, that distance is going to be greater the bigger the atom happens to be. And that's going to happen when you have more and more energy levels, for example, going down the periodic table, or when the outermost energy level is pulled more tightly in as you go from left to right because of more protonic pull. And so keep in mind that these bond lengths are not set in stone. They are average values because neighboring parts of a molecule can affect the length of a particular bond. So, for example, a carbon-oxygen bond in one molecule might have a slightly different length than a carbon-oxygen bond in a completely different molecule because of what the rest of the molecule might happen to be. So we talk about these as average values, and so obviously you're not going to have a lot of significant digits in the bond length. Typically these days we measure our bond lengths in picometers. Remember what a picometer is. It's going to be 10 to the minus 12th of a meter. So there are a trillion picometers in a meter. 10 to the 12th is a trillion. And you can have variations as much as 10% based upon what the rest of the molecule might look like. We can, of course, think about the trends going on. For example, down here, when we go from a single bond to a double bond to a triple bond, you can see that my bond length gets smaller and smaller and smaller. 3 bonds pulling a carbon and oxygen more tightly together creates a smaller bond length than only 1 bond pulling a carbon and an oxygen together, so to speak. So that would be an example of a trend that you might be able to see. When we come over to this diagram right here, you can see that as I go from carbon to the next element on the right, nitrogen, to the next element on the right, oxygen, because I have more protons, my bond length, which starts off at 110, drops by about a factor of 12 and drops again because I have more protons as I go from left to right. And here's a chart of bond lengths. You would not have to memorize these on my test or the AP test. They might give them to you in numbers or in a table or in a diagram kind of like this. So if we're going to be looking at trends, you can see that down here, as we go from a double bond to a triple bond, the bond length gets smaller. Same here, double to a triple bond. Same here, double to a triple. Same here, double to a triple. Those are about the main kinds of triple bonds you're ever going to see. And you also might say, well, how come there's no number right here? Well, this carbon hydrogen can be found right here. So they don't bother showing anything here because that would be a duplicate of everything that's up here. I'm going to erase my squiggles. When we look at the carbonate ion, they're talking about a bond length here between the carbon and a double bonded oxygen, or is it a carbon between a single oxygen? So let's come up and look at carbon oxygen. A single carbon oxygen is a 143. If you come down from oxygen and over from carbon. And a double bond carbon oxygen is going to be a 122. So we have a 143 for a single carbon oxygen and a 122 for a double bond. So when we look right here, our bond length turns out to be 129. And you can see it's in between the 122 and the 143. And that's because, technically speaking, if I were to remove that double bond and to get rid of a couple of those pairs of electrons so that my molecule looks like this, oxygen, 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 2 pairs, 2 pairs, and 2 pairs. And because I took away those two electrons, and that bond represents 2 electrons. I took away 6 electrons, and they're going to be, oh, it just erased. Sorry about that. There we go. So those electrons are going to be located around there, and around there. And so it's technically 1.5, or I should say 1 1/3 bond order. And that's why your bond length is in between the other 2. Now, the third one, it has to do with bond dissociation energy. And dissociation is just a fancy word for breaking the bond. And it's an enthalpy change, the amount of heat that's going to be involved in breaking a bond, but it should also be the amount of energy that's going to be released in the formation of a bond, which is just the opposite, bond association, enthalpy. Notice that this all is taking place in the gas phase, not in the liquid-solid phase. You should also know that breaking bonds are endothermic. You have to put energy in. Forming bonds, which means it's becoming more stable than rather having a bunch of independent atoms in the gaseous state, forming bonds is going to release energy, and that would be exothermic. And so in the battle of breaking and forming bonds, whichever side wins determines if the overall process is exo or endothermic. If it takes more energy to break the bonds than to make the bonds, it's endothermic. If it takes more energy to make the bonds rather than break it, in other words, if you get more energy from making the bonds than it took to break the bonds, then it is going to be exothermic. I hope I said that correctly. So when we look at these bond energies, if we were to use a chart of bond energies and calculate the amount of energy that it takes to break every single kind of bond in a molecule, and then calculate the amount of energy you get when you make every single kind of bond in a new molecule during the course of a chemical reaction, you should get an answer that is in the same ballpark but won't be identical to the way we used to find the overall energy of a reaction when we did the heats of formation of the products minus the heats of formation of the reactants way back in an earlier chapter. So here's something I think I already said. The energy supplied to break a bond should be the same as the energy released when the bonds form. The formation of bonds from atoms or radicals in the gas phase is always exothermic. When you form the bond, it's exothermic. Breaking the bond is going to be endothermic. And so in a molecule like this, it looks like you've got 3 carbon-hydrogen bonds and 3 more carbon-hydrogen bonds that have to be broken. But then when you create this molecule on the right here, you've got the same making of 3 carbon-hydrogen bonds, making of 3 more carbon-hydrogen bonds, but then you're going to be also making a carbon-carbon bond. Well, obviously this and this is going to cancel out that and that, so the net energy is just for the carbon-carbon bond. And again, these are going to be average bond dissociation enthalpies. So if we look at our chart, again, we can look for trends. You can see here as you go from a double to a triple bond, it takes about twice as much energy to break that. Or if we go from a double to a triple here, it takes a lot more energy to break the triple bond than the double bond, as you might expect. The same is going to be true here. In fact, if you look at a carbon-carbon bond, which is 346, there we go. You can see we've gone from 346 with a carbon-carbon to almost doubled, 610 with a double bond, up to 835 for a triple bond. And let's continue on. So, for example, if we're going to look at this overall reaction of propene, remember, ene means there's a double bond. That's what the ene means. We're going to be doing Chapter 10 Organic Chemistry in a couple weeks. And here's my diatomic hydrogen gas. So we have to break a carbon-hydrogen bond, another carbon-hydrogen bond, a double-bonded carbon-carbon, a single-bonded carbon-carbon, and 1, 2, 3, 4 more carbon-hydrogen bonds. Over here, we're going to make 1, 2, 3, 4, 5, 6, 7, 8 carbon-hydrogen bonds, and we're going to make 2 carbon-carbon bonds. And when you take all the energy it takes to break all of those bonds and the energy to break that bond and add it together, and then subtract all of the energy you're going to get when you create those bonds, the net energy change should be very similar to the heat of formation for propane. Here they have a little sidebar on ibuprofen. And just to go off on a bit of a tangent here, without analyzing all of the bonds and so forth, notice that in trying to become more efficient, in trying to stay economically, or I should say in business terms, staying competitive in the manufacturing of ibuprofen once the patent has worn off, people are going to try to find a more efficient way of making it. They want to find another method that instead of taking 6 steps, might take fewer steps. And that would make your ibuprofen cheaper than your competitors, and more people will buy it from you. But there's also some advantages in this type of the right kind of capitalism. I would say there's a way in which capitalism is something that is biblically consistent, and then there are forms of capitalism that are not biblically consistent, as in any form of economics. But because economics is something that is done by people. And the point I want to make, though, is if you can come up with a better way that is faster, or if you can come up with a way that doesn't produce nearly as much waste, it's more environmentally beneficial. Maybe you can come up with a way that doesn't require as many exotic chemicals or complicated equipment, in which case you can make it a lot cheaper. And of course, not only is having less and less stuff that wasted good for the environment, but a lot of times it means you have less byproducts that might be toxic for people. Anyway, let's move right along here. And the overall equation is this, that to find the enthalpy change for any reaction, you take the summation of all the bonds that have to be broken, which would be on the reactants side, minus all the bonds that are going to be formed, which is on the product side. Now, what students sometimes forget is when you're reading these energy values straight off of a table, I don't mean the bond breaking and the bond forming, but heats of formation from a table. It's always a summation of the heats of the products minus the summation of the heats of the reactants. And that is one ugly sigma there. So notice it's products minus reactants. In this case, it's reactants minus products. And I'm going to stop right there. and we have completed the chapter.